Hello everyone, welcome back to my channel. I am Rakshita studying Electronics and Communication Engineering in Sri Venkateshwara College of Engineering, Bangalore. Today we are going to discuss about a topic superconductivity and temperature dependence of resistivity. Let's move forward. What do you mean by superconductivity? Superconductivity simply states that there is no resistance or almost zero resistance in the material or any object. A material or an object that shows such properties is known as a superconductor. The conductivity referred to here is the electrical conductivity of a material. When the electrical conductivity is to the full potential facing almost to completely zero resistance in a material, any of the magnetic flux fields are expelled from the material. The zero resistance is achieved by lowering the temperature of the material, which leads to the decrease in the resistance of the material and an increase in the conductivity. In a superconductor as well, the same method is applied to achieve superior conductivity. Let's move forward to the next slide. Applications of superconductors. Superconductors are noted for their zero DC electrical resistance. Hence, most of the applications of the superconductors examples are because of their properties which provide advantages such as lower power loss because of less dissipation of energy, high speed operations because of the zero resistance and continuous flowing electrical current and high sensitivity. The usual and well-known superconductor examples are mercury superconductors, niobium tin superconductors, lanthanum barium copper oxide superconductors, and yttrium barium copper oxide superconductors. Example of application of superconductors include medical MRI/NMR devices, magnetic energy storage systems, motors, generators, transformers, computer parts, and sensitive devices for the measurement of the magnetic fields, electrical current, etc. Future possible applications involve high performance smart grids, electric power transmission transformers, electric motors in vehicles like maglev trains, magnetic levitation devices, superconducting magnetic refrigerators, etc. Let's move forward to the next one. Disadvantages of superconductors. Although useful in a diverse range of applications, superconducting materials are active only when they are kept at a low temperatures. Every superconducting material has a temperature below which it becomes active. The temperature is called transition temperature. Keeping them below the transition temperature involve a lot of expensive cryogenic technology. Hence, superconductors still do not show up in most everyday electronics. Scientists are researching way that can make such superconductors operate at our room temperatures. Let's move forward to the next slide. Temperature dependence of resistivity. What is resistance? Resistance is the obstacle to the flow of electrons in the material when the potential difference is applied across a conductor. It helps for the moment of the electrons while resistance opposes the moment of the electrons. A combination of those two factors is the rate at which charge flows between two terminals. When a voltage is applied across a substance, an electrical current is produced. The voltage applied across the substance is through it directly proportional to the current. The proportionality constant is called the resistivity of the metal resistance, V equal to Ri. Hence, resistance is defined as the ratio of the voltage applied to the substance to the current. Resistance is measured in ohms. What is resistivity? Resistivity is basically the quantitative value of the resistance offered by any material. Although materials resist electrical current flow, some are better than others to conduct it. Resistivity is the figure that allows comparisons of the how different materials allow or resist current flow. The SI unit of the resistivity is ohm meter, commonly represented by the Greek letter rho. The resistivity of the material can be defined in terms of the resistance R, length L, and the area of the material A. From the equation, it can be seen that the resistance can be varied by adjusting a number of parameters. Temperature dependence of the resistivity in metals. The resistivity of the material is temperature dependent. The temperature of the dependence of the resistivity is different for the conductors, semiconductors and insulators. In conductors, as temperature increases, the atom starts vibrating heavily, leading to the collision of the free electrons and the other electrons. This collision causes a loss of energy from the free electrons, which are responsible for the current flow. The reduction in the energy increases the resistivity of the conductor, especially metals. As the temperature increases, the resistivity of the metal increases as well, giving it a positive temperature coefficient of resistance. At high temperature, the conductor resistivity increases and the conductivity decreases. As per the Matheson's rules of the resistivity of any metal at a given temperature is the sum of the resistivity due to lattice vibration and due to impurities. The total resistivity is given by rho T equal to rho naught plus rho of T. You can see the graph on the screen plotted against temperature versus resistivity. Temperature dependence of resistivity in superconductors. In superconducting materials, the resistivity suddenly drops to zero at a particular temperature known as critical temperature and remains zero below that as shown in the figure. The critical temperature for the mercury is 4.2 Kelvin. Below this temperature, mercury is in superconducting state, whereas above this temperature it behaves like a normal conductor. Different superconducting materials have different critical temperatures, but the nature of the variation in resistivity with temperature remains more or less similar. Critical temperature. Temperature at which the resistivity of the material drops to zero is called as a critical temperature or transition temperature. Example, Hg equal to 4.2 Kelvin, Pb equal to 7.2 Kelvin, Nb equal to 4.5 Kelvin, yttrium, barium, copper oxide equal to 92 Kelvin, etc. You can see the graph plotted against Tc versus rho. General properties of superconductors. It is a low temperature phenomenon. The transition temperature is different for different substances. Materials having high normal resistivities exhibit superconductivity. For chemically pure and structurally perfect specimen, the superconductivity is very sharp. Ferromagnetic and anti-ferromagnetic materials are not superconductors. Below the transition temperature, the magnetic flux lines are rejected out of the superconductors. Superconducting elements in general lie in the inner columns of the periodic table. Those metallic elements having their valence electrons lies between 2 to 8 exhibits superconductivity. Below the transition temperature, the specific heat curve is discontinuous. Misner effect of magnetic field. When a weak magnetic field is applied to the superconducting material and then cooled below the critical temperature, then magnetic flux will be expelled out of the superconductor. Thus, the superconductor show perfect diamagnetism. This effect is reversible and the specimen returns to its normal state when its temperature raised above its critical temperature. We have the magnetic field inside the specimen B equal to mu naught H plus M. H equal to applied magnetic field and M equal to magnetization in the specimen. According to Misner effect, when the specimen is in the superconducting state, it has B equal to 0, thus H equal to minus M. Magnetic susceptibility equal to M divided by H, that equal to minus 1. This is the indication for the perfect diamagnetic material. You can see the diagrams on the screen. Field or critical magnetic field. It is defined as the magnetic field required to switch the material from superconducting state to the normal state, and it is denoted by Hc. When once the applied magnetic field is removed, the material will regain its superconducting property provided T lesser than Tc. Thus the material will remains in the superconducting state below Hc, and above Hc the material will be in the normal state. Let's move forward to the next slide. Temperature dependent of the magnetic field. Hc. Magnitude of the Hc depends on the temperature. If H naught is the critical magnetic field at T equal to 0 Kelvin and Hc the critical magnetic field at T 0 Kelvin, then Hc equal to H naught 1 minus T divided by Tc whole square. It can be seen that the curve of the Hc versus T is almost parabolic. If the superconductor is held at 0 Kelvin, then the higher magnetic field is required to destroy the superconducting property. When the temperature of the superconductor is close to Tc, then to lesser, magnetic field is sufficient to destroy the superconducting property. You can see the graph on the screen plotted against T divided by Tc versus H. Types of superconductors. The classification is based on the response shown by the superconductors in the applied magnetic field. The response curve of the magnetization versus applied magnetic field show a different nature of a variation for the different category of superconductors. This classification provides useful information for the selection of the superconductors in the development of the high field magnetic fields. Type 1 superconductors, soft superconductors. They exhibit complete Misner effect. Material in the superconducting state retain its diamagnetic nature until the critical field is reached. Once the critical field is reached, the material suddenly loses superconducting property. Here onwards, the flux starts penetrating the specimen. These superconductors have low critical magnetic field. They are not useful for the construction of the superconducting magnets, example Hg, Pb, Nb, Sn, etc. You can see the graph on the screen. Type 2 superconductors, hard superconductors. They do not exhibit complete Misner effect. They are characterized by two critical magnetic fields, namely lower critical field Hc1 and upper critical field Hc2. For the applied field less than Hc1, the magnetic field is completely expelled out of the superconductor and it behaves as the perfect diamagnetic. When the field is greater than Hc1 and less than Hc2, the flux starts penetrating the specimen. In this region, the material is not perfect diamagnetic but still retains zero resistance. Hence, it is called as a mixed state or vertex state. When the applied field exceeds the Hc2, all the flux will penetrate the specimen and the material becomes a normal conductor. Example, compounds like YBaCuO, BiSrCaCuO, etc. You can see the graph on the screen. Theory of superconductivity. It is the quantum mechanical theory to explain superconductivity. According to this theory, superconductivity is due to the formation of the copper pairs. Copper pairs are the pairs of the electrons formed by the interaction between the electrons with opposite spin and momentum in the phonon field. Flow of current in a superconductor causes attraction between the electrons and the positive ions. Due to this, the positive ions get displaced from its position. When the second electron reaches the disordered position, it also experiences the attractive force. Thus, we have attraction between two electrons that takes place via lattice. This pair of electrons forms copper pair. In a given superconductor, each copper pair causes the formation of many number of such pairs, causing the formation of the cloud of copper pairs. Due to the orderly motion of these copper pairs in a group and less collision with the lattice, large current is produced. When the temperature exceeds Tc, there is no formation of the copper pairs and the superconductivity destroys. Let's move forward to the next topic, high temperature of superconductors. Superconductors that exhibit high Tc are called as a high temperature superconductors. Generally, those superconductors that can work at liquid nitrogen temperature above 77 Kelvin are classified under high Tc superconductor. They are oxides of copper bearing peroxide crystal structure. Example, barium copper oxide, yttrium barium copper oxide, etc. Recently developed high temperature superconductors are from the ceramic compounds. All the high temperature superconductors are classified under type 2 since they have higher critical magnetic fields. The current in the high temperature superconductors are direction dependent. The currents are maximum in a direction parallel to the copper oxide planes. Supercurrents are minimum in the direction perpendicular to copper oxide planes. Thank you for watching my video. Please like, share and subscribe.